In this video, we're going to start talking about friction. And friction's incredibly important in prospecting because of the two forces that are principally involved in determining where gold ends up, friction is often the most important one. Well, g'day. Welcome to Mad Scientist Prospecting. My name's Stuart Chignall, and this is episode 3 of the Fluid Dynamics of Prospecting. Now, the main point of this video is to show you how powerful an effect friction can be and how present it is in any system at all, really. Now, I'm sure you're familiar with friction between solid objects, but I'm not entirely confident that you would be aware, or that everyone would be aware, that a friction occurs between any two things and not just between solid objects. But even those people who didn't already know that, I'm sure you're familiar with the terms drag and wind resistance. And those are just specific names for friction to do with air and to do with water. Now, we can't see friction, but we can see its effects. And I've got a series of demonstrations to show you that demonstrate how powerful a force friction can be. And this is the same setup as before. The hose is just turned on. We've just got to full flow coming out of the outlet. And this point here is the halfway mark. This is maximum pressure. So from the halfway mark to this point, we've doubled the pressure. But you can see that we haven't doubled the distance that the water is being thrown from the spout. And we can infer from that we haven't doubled the velocity. Now, all the relationships that we've talked about so far have all been linear relationships. A linear relationship is when you draw it on a graph, it forms a straight line. The relationship between flow and velocity is a linear relationship. Double the velocity, double the flow. Same with area. Double the area, double the flow. But the relationship between friction and velocity isn't linear. In fact, friction is proportional to the square of the velocity. And what that means is if you increase the velocity a little bit, you increase the friction a lot. Here, okay, we've got a really short pipe. And now I'm going to replace this pipe, a much longer pipe. You can see how much it's reduced the flow, and that's because of the friction. Because friction is proportional to the surface area where the interaction occurs. Now, in episode 2, I said that for every pressure, there is a particular velocity. I'm not sure that I mentioned that the converse is true. For every velocity, there is a particular pressure. Now, in this system, with this longer pipe, the pressure in the bucket hasn't changed. If it's a 400 ml deep bucket, it would be 0.04 bar. If I was to measure the pressure at the outlet, it would be drastically reduced. And this drop in pressure that you see from the start of a pipe to the end of the pipe is often referred to as, the cause is often referred to as back pressure. But it's not pressure. It's got nothing to do with pressure. It's actually friction. We're going to be talking about friction in pipes when it comes time to doing the fluid dynamics of designing equipment like high bankers and stuff. But right now, I just want to get across a couple of things. Now, you would have heard that everything has an equal and opposite reaction from Newton's laws of motion. Again, something we'll be talking about in another episode in more detail. When the pressure level in the bucket, when the depth is increasing and that pressure is increasing, more and more force is being applied to the water at the bottom of the bucket to force it out the outlet. As that's occurring, the velocity is picking up, and at the same time, the friction is increasing. And the two are always in balance. The friction is always impeding the flow of water. And as the flow of water is increasing, so is the friction. And that's how we get equilibrium in the system. Once the pressure level gets to a certain point, and the flow gets to a certain point, the velocity gets to a certain point, the friction gets to a certain point, and everything is in balance. And I'm sure you know this, you just know it by a different name, and that's terminal velocity. If you jump out of a plane, the force of gravity accelerates you towards the earth. You're getting faster and faster and faster. But as you do, the friction is increasing, the drag, the air resistance is increasing. And it'll get to a point where the reactive force of the friction will balance the active force of gravity, and you'll stop accelerating. You'll still move at the same velocity, but you'll no longer be accelerating. And at that point, your fall will be in equilibrium. Your position won't be. And unless you do something, you'll go splat. Something like deploying your parachute. And all that a parachute does is massively increase your surface area, which massively increases your friction, which massively reduces your terminal velocity, so that when you get to the ground, you don't go splat. And that we'll go into in a lot more detail in another episode. But if we were to measure the pressure at the bottom of the bucket, when the bucket's full and overflowing, it would be around 0.04 bar, because there's 400 millimeters of water creating the pressure. But if we had a pressure gauge on the outlet, the pressure there would be vastly reduced. So just as I was saying in episode 2, that every pressure has a specific velocity, the converse is true. Every velocity has a specific pressure, because the friction is impeding the flow of water along the pipe. The pressure at the outlet doesn't correspond with the pressure at the bottom of the bucket. It corresponds with the velocity at which the water is moving at that point. Yeah, not quite. Well, not exactly. It's more complicated. You've got different things causing different pressures. Now in the bucket, the water is actually moving at a velocity. It's a very, very, very low velocity, because the area of the bucket is huge relative to the flow. And so the pressure that is there corresponds with the depth of water that's in the bucket. Because the hose, or that little pipe outlet, which is where the water is exiting the bucket, is horizontal, at the end of the pipe, there is no added pressure due to any further depth. If the pipe was running down, then there would be a component of the pressure at the outlet which would correspond to the depth of water. The depth of water in that case would be the water level in the top of the bucket versus the outlet of the pipe. But that gets a bit tricky, and we're going into this in more detail in another episode. But basically, you've got static pressure, dynamic pressure. Dynamic pressure is related to velocity, and that's the velocity I'm talking about, which corresponds with a particular velocity. And static pressure is relating to a pressure from another source, in this case gravity, although it could be the pressure from the impeller of a pump. Again, we'll get into that later. So I hope that makes sense. This is probably one of those things where I might need to answer some questions. Because for every pressure, you have a corresponding velocity. For every velocity, you have a corresponding pressure. That's going to be very important in a later episode. But now I want to show you a system where the friction's minimal. So what we're going to do is take away these pipes, and we're just going to go with the very, very short pipe that I mentioned in episode 2. The short pipe, which is just the hole in the bucket, where the pipe length is equal to the wall thickness of the bucket. Now, because friction is proportional to the surface area involved, and because this pipe is so short, like it's this long, then we can basically say that the only friction is from the water entering the pipe and exiting the pipe. Because now we're going to increase this pipe size by drilling a bigger hole. This is the water spout from the bucket full at 19 mil in diameter. This is the water spout from the bucket at 25 mil in diameter. Now the difference in friction between these pipes is minimal. And you can see that by seeing how closely the water spouts align with each other when we superimpose the images. And you can see that basically there's no difference between them. Now simple systems like this make it easier to see those relationships. Relationships that in a creek or a river, or even something relatively simple like a sluice, get covered up because you have changes in velocity, changes in fall, changes in area, which make the system much more complicated. I really hope that those demonstrations make sense, because I've got to get it across to you that velocity and pressure are intimately linked, and that friction is so pervasive. Anywhere you have anything in contact with anything else, you have friction. And that is crucial to understand, because you don't just get friction between water and a solid surface of the riverbank or the sluice, but you also get friction within the water itself. And that's crucial to understand when we start talking about different types of flow, and in particular, laminar flow, which we'll be talking about in the next episode. Well, I hope that all made sense. If it didn't, then please ask your questions so I can explain and clarify, have a second attempt at communicating what I'm trying to get across. And if you're not already subscribed, make sure you hit that subscribe button with the bell icon so that when the next episode comes out, which should be next Wednesday, you won't miss it. And as always, you know, like and sharing is caring. There's a lot of work that goes into putting these videos together. It's quite odd. Before doing this series, I was producing 2 to 3 videos, 4 videos a week. Since I started the series, I've struggled to do just one. So yeah, it'd be great if you could share the message around. But anyway, have fun, and I'll see you next week. Bye-bye.